How's the audio? Is this okay?
We're going to ask the folks really, really long delay. Perfect. Ladies and gentlemen, thank you for coming out to Noisebridge this evening. I'm going to hand it over to my front man here, my partner in crime, Neil Pandya. He's going to do his splendid intro as usual. We've got two excellent talks tonight. I'm really excited. Hopefully you are too. So without further ado, take it away, Neil.
Good evening, everyone. My name is Neil Pandya. I would like to welcome you all to the 11th monthly Cyberspectrum meetup. This event serves as a forum for the exchange of knowledge and ideas related to software-defined radio, and generally aims to get people interested and excited about the applications that can be realized with SDR technology. Engineers, students, hobbyists, enthusiasts, and people of all experience levels are welcome no matter what your hardware or software background. At each meetup, people from the community will have the opportunity to present their work, projects, and ideas to the group. The event here tonight is being sponsored by Bastille Networks and hosted by Noisebridge. Our first speaker will be Colby Moore, who will give a presentation titled Spread Spectrum Satcom Hacking, Attacking the Global Star Simplex Data Service. Recently, there have been several highly publicized talks about satellite hacking. However, most only touch on the theoretical, rather than demonstrate actual vulnerabilities and worldwide attack scenarios. This talk will demystify some of the technologies behind satellite communications and take the audience step by step from reverse engineering to exploitation of the Global Star Simplex Satcom protocol. In recent years, Global Star has gained popularity with its introduction of consumer-focused spot access tracking solutions. Colby will deconstruct the transmitters used in these solutions and reveal design and implementation flaws. Colby Moore is SYNAC's Manager of Special Activities. He is a former employee of VRL and has identified countless zero-day vulnerabilities in embedded systems and major applications. In his spare time, you will find him focusing on that sweet spot where hardware and software meet, usually resulting in very interesting consequences. Our second speaker will be Nate Temple. Sorry, did I say first? Our second speaker will be Nate Temple, who will give a talk titled Etch A SDR. He will do a quick show and tell building the Etch A SDR, which is a digital Etch-a-Sketch that doubles as a fully contained SDR platform. Nate is a programmer by day and an SDR enthusiast, hobbyist by night, as well as a maker and amateur radio operator. The meetup presentations will be recorded and posted online and will be streamed live on YouTube. The previous 10 events have already been posted in full HD video. We have set up a channel on IRC called #Cyberspectrum on Freenode as a way for people remotely watching the live stream to contact the group here in San Francisco with any comments or questions, as well as to alert us to any audio-visual problems. Future meetup locations will alternate every month between here at Noisebridge in San Francisco and the Edis Research Office in Santa Clara. The meetup next month, October, will be postponed due to travel obligations for the organizers. Cyberspectrum will resume again in November, tentatively on Wednesday, November 18th, at the Edis Research Office in Santa Clara. Further details will be posted on the meetup page about 1 or 2 weeks prior to the event, so please tune in, pun intended, for all the details, including a list of speakers and presentation topics. As always, if you would like to present something, or if you have any ideas about future topics, then please let us know. We would like to thank all of our speakers tonight for their efforts and enthusiasm, and we would especially like to thank Noisebridge for providing the space and hosting the meetup, as well as Bastille Networks for providing complimentary pizza and soda. We'll now get started, and I'll invite our first speaker to come forward. Thank you.
Thanks, Neil. So I do apologize to you, Neil. We made a final, very last-minute scheduling change. We're going to have Nate as the first speaker. That's what I was trying to whisper to you. So you're good to go? We just need to switch to HDMI?
Yep, we'll just switch this.
So I actually think that we need to just do that, and then it'll search and find you as long as you're outputting a valid signal.
It's all good, at least in Canada.
No signal?
Patch gone wrong.
HDMI switcher, VGA source. Floor HDMI. Hang on. So we have to do. Let's try. This. There we go.
So thank you for having me speak about building the Etch A SDR. So, my Twitter account there, and then you can find all the code for this on my GitHub page. So first, a little bit about me. I'm a programmer, SDR enthusiast, and hobbyist, amateur radio operator at Interest in Satellites. Big fan of Cyberspectrum. Been watching them.
And you've flown in all the way just to be here, right?
Yep, the flights were very cheap, so I was able to do that.
How good is that? We're going to run off applause for that. Thank you.
Some of my goals for building this project was I wanted a mobile SDR unit. I wanted it to be low power and battery operated. I wanted knobs and buttons to control GQRX. And I wanted to run GQRX on an ARM, small like Raspberry Pi type board. Wanted something to introduce people to SDR with because I'm always talking to people about SDR. Won't shut up about it most of the time. And I want to have fun and build something cool. The main features of it, there's an SDR mode. So that runs GQRX. The knobs adjust the tuning frequency. Each knob on each side has a different stepping position. There's red buttons on the sides, which I'll have a slide. They increase or decrease the knob's step position. The black buttons adjust the debond mode that's selected, and then it also powers off the unit. There's a game mode, which runs as a full Etch A Sketch. So the hardware that I built this with was a Odroid C1. It's a Raspberry Pi type board, a little bit more powerful than the Raspberry Pi V2. There's also a Teensy 3.1 microcontroller in there, rotary encoders and buttons, 10.1 inch screen. There's a gyro in there, RTL SDR, some acrylic sheets, and then got knobs from a real Etch A Sketch, which was hard to find. Here's kind of an overview of the hardware. The Teensy handles the gyro, the knobs, and the buttons. Passes all those messages on to the Odroid. Odroid's hooked up to an external USB bulkhead Ethernet adapter. Also has a screen, and the RTL SDR plugs into the Odroid with an antenna. Then there's it can run either on an AC power adapter, or it will also run on a 3S LiPo. There's also a 12 volt to 5 volt DC step down converter in there that powers the Odroid. Here's a picture of the left side, and then a picture of the right side. And inside is kind of a nest of everything. So for the software, it runs Ubuntu 14.04, GQRX, which is a modified version. I've added some extra gain controls that are adjustable through the Telnet interface. GNU radio takes 8 hours to compile on the C1. Node.js and Socket.io, that's for the Etch A Sketch side. Uses Redis, Python, Pi user input, which clicks the UI buttons. I haven't gotten to modifying GQRX yet to take certain inputs, such as like starting in full screen mode and auto starting. So the Pi user inputs, clicks those UI buttons. And found the game Etch, which is almost complete. I started with that to create the Etch A Sketch game. So in the software mode, for the SDR mode, the teensy is hooked up to the Odroid, runs GQRX. Bash script reads the startup file, determine mode, launches the GQRX process. Pi user input script clicks the UI buttons. So it's the start button, it enables the telnet control and puts it into full screen mode. The teensy monitors the knobs, buttons, and the gyro, passes those messages to Odroid by serial interface. There's a Python script that parses the teensy messages and passes those messages on to GQRX. For the Etch A Sketch mode, almost the same setup. Bash script reads a startup file to determine the mode, starts a Redis server in the Node.js app, launches a Chromium browser, so then teensy monitors the knobs and the buttons and the gyro, passes those messages, just the dumb messages on to the Python script. Then instead of sending it off to telnet, it publishes the messages to Redis, pub sub on Redis, and then the Python script monitors for a shake. So then the Node.js app subscribes to the Redis feed. It broadcasts those messages via socket.io out to the browser, and it draws the pixels on an HTML5 canvas and clears the screen on the shake. So then here's part of the laser cutting. This is the first version that I kind of was putting together. So the speakers are still on the side, and I made it out of wood initially. And then here's a more final version with the acrylic. Here's a demo of Odroid C1 running the GQRX, just so you can kind of get an idea of its responsiveness. It's not bad for a $37 computer. Okay, so live demo. Plug it in, power it on.
While you're setting up, where did you get the laser cutting done?
What's that?
Where did you get the laser cutting done?
At the Sin Shop, Hack Shop Makerspace in Las Vegas. Member there, and they have access to the laser cutter, which is a huge benefit of being part of the makerspace. Takes a second to boot. So then the Pi input's gonna run along and hit the buttons. I gotta just add the change GQRX to allow those startup flags. So then each knob I don't have that great of an antenna here. With a better antenna, they pick up the FM. So then, if you press and hold this button, it'll put it into the Etch A Sketch mode. live demos. I'm sorry. Alright, you can just shut it off. So now it should boot into the Etch A Sketch mode. So the knobs will adjust it 1 pixel by 1 pixel. The red buttons on each side will adjust it by 4 pixels at a time, so it's a little bit faster.
How long did it take you to make this?
Couple weeks. I mean, like on, you know, after work and weekends. Man, there's this just sketch mode. All right, we're gonna have to skip that. Although it's one of the cool parts because it.
You plug in your wireless mouse.
Yes. Live demos, I'm sorry.
If for some reason it doesn't work, no pressure at
Yeah.
all. You can
Just
come back
yep. It should
once you get it working.
it should boot this time. Thought I had all the little bugs worked out of it, but
Live demo is the perfect place to find the rest of it.
Have you showed this to Alexandru? You wrote GQRX?
I just
no, I haven't. I want
He'll
to
dig this.
tweet it to him. Yeah. Okay, so it's launching the Chromium browser. And then, probably can't see that on camera, but Etch A Sketch, and then
Do we have a go?
yeah, I'll put that up and you guys can play with it. And so, for the future, I'd like to make a not Etch A Sketch that's maybe a little bit smaller, like handheld one. There's a new Odroid, the XU4, and I'd love to see Phosphor run on it. It has the open GL like ARM version of that. So Phosphor would take a little bit of porting, but that'd be really neat to see something that uses a GPU. Maybe put a different SDR in there, like a Hacker Alpha or a Blade. Be able to TX with it, kind of like what the plans are for the Portapack. I'd like to add some shielding to this specific one and expand GQRX to have the better startup options. And then some more games that, you know, there's the buttons on the side, so I'd like to do some other games with that. Here's some links. You can get the Odroids at hard kernel, otherwise Ameridroid is the US shipper. The Teensy 3.1. I got all the buttons and screen buttons and rotary encoders from Adafruit. There's a laser link, but I believe they have a laser cutter here too, so if you're not a member in Noisebridge, that might be an option for you. All the code is right there under my GitHub. Special thanks to the Sin Shop, Hackerspace. If you guys are ever in Vegas, come out and stop by. Couldn't have built it without being a member there. And it's always great to be around, like-minded people. Especially Brian M. He was initially helping me with the laser cutter setup, and he was like, "You should make this. You could get some red acrylic and make it." And I'm like an Etch A Sketch, and then that's where it's pretty much born. Julian on IRC, he had helped me with a couple of GQRX mods. The RTL SDR people and New Radio people on IRC are always very helpful. And Noisebridge, and then Cyberspectrum. Thank you guys for having me. And then that's it.
Thank you. How was working with the Teensy?
They're really nice. I mean, for like $20, they blow away our Arduinos. And they, for $20, it's like you can overclock them up to 96 megahertz. And then they also have multiple serial inputs. Like I have another project for a quad that takes, it's like a telemetry unit, and then it sends it over to these little RF links. And I needed multiple serial links for it, and the Teensy worked really great for that, versus a regular Arduino only has one. So, is there any other questions at all? Yes. Yes.
You talked about shielding.
Yep.
How effective is it by all the wires and
It,
microcontrollers and that?
you can see, like this particular screenshot, the noise floor is really low. Once it's in there, because there's like the HDMI. Oh, sorry. This doesn't, it's not great, but it's better. But there's the video. The dark blue board there is the video controller for the screen, and that's really noisy. And then, those little 1-inch RTL SDRs are not that great. And then too, I notice if I depending upon the antenna too, if I hold on to the ground of it, it'll improve it. So I'm assuming if I attach the grounds in there, it'll help it. And those little RTL SDRs, it's like the crystallinum will drift. You didn't really see it on there, but I could show you. They'll tend to drift quite a bit. So it would be nice to see, like put the RTL SDR away and get it away from I always notice HDMI lines are extremely noisy, like around the 70 centimeter band.
You can wrap your RTL SDR in aluminum tape. I found that works really well for shielding.
Yeah, I should try that, and then I don't know if I need to, if I have like a ground loop or something if it would benefit from grounding the main ground to my antenna ground too on this unit or not, but
There are also the fancier RTLs that come in a nice metallic case and apparently have a PCX on the side.
Yep.
And that's still fairly compact.
Yeah, that could be. If I took apart the USB lines maybe, or maybe reorganized it a little bit, like it's all just kind of stuffed in there. I should be able to get enough room. I initially started with a regular full-size RTL SDR, and I ended up desoldering the USB connector and then directly wiring a USB line onto the PCB board. But then I was like, oh, this is a hack job. I'm just going to order one of the little 1-inch ones and call it good.
Have you run this off of a battery pack?
I have ran it off of a 20 amp 3S battery. I got about an hour and a half off of it.
Did you go mobile?
Just like around the house, it works. And
Because I could imagine you taking this out to various interesting places and having a bit of fun and potentially getting some interesting looks as well.
then I want to set it up the software so I could just like switch modes really quickly instead of having to do the reboot process. The it's a tablet. I mean, it's like a tablet with knobs. So if I wanted like go like sniff RF stuff in public, I'd just probably take a tablet versus this big thing. But if I could switch in SDR mode, I'd into Etch A Sketch mode, just playing the game, you know. Minus the antenna. That's one thing. I have the little GSM antennas, which look cool on the side, but they don't really work for anything other than GSM.
Could you somehow embed an antenna into maybe the
Definitely, yeah. I
side
could,
of the back of the unit,
like
Part of the unit evolving.
yeah, I could do like the WA5 EJB log periodics. Could just like stick it right on the back or something. That would work. That's kind of one thing I like wanted to do with it. Maybe it was like not exactly direction finding, but just be able to say, oh, it's stronger that way. And with the WA5 VJB log periodics. Yes.
Is the, you had a motion sensor, is that mostly just for the shaking, or are you using it for the SDR as well?
Yep, that's only for the shaking of the Etch A Sketch mode. That's still, there's kind of the thought to maybe add that as a feature, like gesture motions. But actually, I have it just commented out so that it's only just spitting out the accelerometer data. So then if I, see enough of a difference between the last 5 samples, then it will send it the shake alert. But it would be cool to do certain gestures like volume or something, because and that was one thing. I have a power button that just shuts it off. I had initially planned to do that, to switch mode, so I could switch it, the like gain, adjust the gain, adjust the audio gain. But it just does the modes and then the frequency steps.
If you wanted to be really surreptitious with your switch between radio and Etch A Sketch, you
Yeah.
could even just detect like a double tap,
Sure.
and then it doesn't look like you're reaching to press any
Yeah,
buttons or anything.
yeah, I could. Yeah. I kind of ran into the speed at which the accelerometer is spitting out data. It will jam up the Redis and Node.js pub sub. And I don't know if that's just, probably streamline that. There's probably a better way to do that, but I just used what I knew and kind of like hacked each part together and made everything work. But I know there's ways to streamline a lot of that code. So, but it was just like I wanted to get each step done and then go back and fine tune it.
Very nice.
So-
All right. Any other questions from the audience? All right. In that case, let's thank our speaker. Some very cool hackery there. Thank you very much, Nate. So while we have our second speaker, Colby, set up, a little bit of time for some announcements, and I believe we certainly have one queued up. Josh, you want to come down here? Josh has an announcement.
Yeah, so more of a question. I've been doing a bit of contract work with some folks on a device that they were having some problems with noise on. So I'm like, oh, okay, I do radio stuff. I'll have a look at that. And then I realized that I can't find a broadband sampling, like anything for GNU Radio. Has anybody done that with their usurp and published it online? I did some stuff pretty quick in IPython. I guess that's why nobody does it, but if anybody knows about that, or why they haven't done that, or why they haven't published it, I would love to hear about it. And I'll be around after we're all done.
So can you explain a little bit more what you're looking for, Josh?
Oh, yeah. So specifically, I need a spectrum analyzer, but I don't have $2,000 lying around because I spent $1,000 on my usurp. It seems like my usurp should be able to get all of these samples in and kind of, you know, see what's going on.
Is RTL power do that for you?
RTL power will do it, but I need to do it over rather a lot of spectrum relatively quickly. And I also want to go places that the RTL SDR doesn't want to go. But yeah, a lot like RTL power.
Usurp spectrum sets.
Yeah, there used to be a script called user spectrum that would do exactly that and step through everything.
Okay.
I don't know its status or how long
It,
it's
it,
updated.
it still exists. It's in the remote.
Okay, cool. It's probably doing more or less what I wound up doing because it's pretty trivial. I just don't know why it wasn't out there. So maybe it was and it's just out of the way. Anyway, cool. Anyway, I'll be around to talk more about it. Thank you for that, though. That's super helpful. Cool. Thank you.
Okay, so we'll now kick off with our second talk. You ready to take it away, Colby?
Why not?
All right, so here's Colby Moore talking about spread spectrum satcom hacking.
How's this thing work? You guys hear me all right?
Yeah.
Cool. Uh-oh. I think I broke it. And all right, we're back. All right, hey, good evening, everybody. Thanks for coming out. Tonight, I'm going to talk about spread spectrum satcom hacking and hacking specifically the Globalstar Simplex data network. I gave this presentation at both Black Hat and DEF CON, if you guys are familiar, earlier this summer. It's kind of the big hacker conferences of the summer. So I'm going to be approaching this from kind of the topic, from the perspective of a hacker. So feel free to ask questions or jump in if you guys have any questions about terminology or where I'm coming from here. But first, a little bit, who am I? My background, I'm actually a mechanical engineer, but I love computer security. I currently work at a company called Synac on the R&D team. Basically, I just get paid to hack stuff all day long. I first got interested in satellites and radios when I was a lot younger. I got my ham radio license, and that kind of kicked things off. I don't really have any formal SDR education going into this project, but I was able to kind of learn pretty quick. There's some great resources out there. I'll try to point you guys to those. And it ended up working out really well. So my office was kind enough to sponsor this research and sponsor me, send me to Vegas to give this talk. So I wanted to give a thank you to my company, Synac. Basically, we're on a new spin on security for the enterprise. We have a bunch of like vetted security researchers that we let hack our clients for bounties. So if you guys are into security research, we'll pay you to hack our clients. Or if you need security help, maybe we can help you out. So first, a little bit of an introduction. I've been pretty frustrated with the lack of talk diversity at the security conferences and kind of wanted to try my hand at something new. And as a hacker, like satellites are kind of the ultimate hack. And there seems to be a satellite hacking talk once every year or so. But they're usually very theoretical and don't demonstrate like that someone could actually do something. So I've been doing a lot of research on location-based privacy at Synac. So I thought looking at satellites that monitor people's locations and such seemed like a good idea. Bottom line, I want to take a stab at something different and hopefully inspire and collaborate on some further research in an unexplored area. I'll also be releasing some tools, so hopefully you guys can take a look at those. So what are we going to learn? We're going to talk about a little bit about the basics of RF signals and modulation. What is spread spectrum? Then we're going to select a target and reverse engineer it, and hopefully exploit that target. So my goal in doing this research was to do it all for about less than $1,000. Keep it all very accessible to the hacker community, to the maker community, for anybody who wanted to try their hand at some crazy SDR stuff. There's a lot of material to cover, so I'll try to go really fast. If you guys want me to skip or elaborate, let me know. So my intent was to keep this all very high level, but give you guys enough detail to kind of see what's going on. Really, all you really need is a high school mathematical knowledge and some familiarity with computers, and you should be good. So assuming we want to hack a satellite, how do we pick the right one? There's lots of potential targets out there, but picking the right one is really key. Considering I had a really minor budget and satellites are inherently difficult, I wanted something that was consumer accessible, cheap, kind of popular and widespread. Whatever I hacked, I wanted to have like a really widespread impact.
So I was familiar with a company called Global Star and their Spot line of consumer products. I use them while backpacking. And I personally think the products are great. They make asset trackers for like tracking your car or yacht, or what they call personal locator beacons for when you're out in the wild. So you press a button and it calls for help, and the search and rescue guys come and save you. So I started digging into their tech, and it turns out that their commercial offerings, their consumer offerings are the same as kind of the commercial offerings. All the tech is exactly the same. So basically, I could buy a dirt cheap device to research that was intended for the consumer, and the research would translate into the more expensive devices out in the network, even military devices and such. So up here, I got an example, a couple of devices. On the left there is the Spot Trace. You guys can come up with it later. It's a asset tracker that you can put on your car. This is a professional quality asset tracker. These are strapped on almost all the shipping containers flying around the United States right now. In the center, the one on the far right is one of the personal locator beacons. So where is this satellite communication technology used? Really, it's used everywhere. It's designed to be integrated anywhere low bandwidth off-the-grid communications are needed. I think the most interesting applications are used in SCADA systems. Big oil and gas companies eat this stuff up. They're using it for tracking all their assets and monitoring their stuff. Military applications, and then largely and mostly asset tracking, think shipping containers, or armored cars, or other interesting things like that. So all this tech operates on what's called the simplex data service. But how does that work? In the case of, let's say, one of these asset trackers, the devices can also send back arbitrary data as well, not just coordinates. The asset tracker gets its location from, it has a GPS on chip on board, gets its location from the GPS constellation. It then beams that location back up to the Global Star satellite. A satellite beams that information back down to Global Star ground stations, which then interpret the data and forward it on the internet to the user, to the cloud, wherever it's destined. I kind of liken the service to SMS for the satellite world. Just think short and sweet, simple messages. So the Global Star system is a series of low Earth orbit bent pipe satellites. And the way a bent pipe satellite system works is it simply repeats the data it hears. It doesn't demodulate or decode the signal. This keeps the cost of the satellite really low and future usability pretty flexible. So really, it's hearing us transmit our data on the ground and just sending exactly what it hears back down. But notice the data link in this case is one directional, a simplex data network. So how the heck is that reliable? Well, it turns out that each data packet from these devices is sent multiple times. After giving my presentation, I talked to some experts on this Global Star system. It turns out when they first deployed their satellites, they didn't do a good job radiation hardening them. And it was originally intended to be a duplex link for cell phone sat phones. And they threw these satellites up right in the middle of the Van Allen radiation belts, and half of the data link died. All the satellites just burnt out. And so they had to have a nice little marketing spin and repurpose the satellite system into the simplex service that they advertised so highly. So it's a really good engineering save on their part. So what's the deal with these ground stations? It turns out there's hundreds of them. Actually, I think maybe the real number is more like 40 of them around the globe. And they handle the reception of satellite data. And then there's two main control centers. One here is actually based in San Jose that handle kind of the fleet management, positioning, and monitoring of the health of the satellites. So here's a coverage map from Global Star's website for the simplex service. You can see that there's patches with no coverage, and that's because there's no ground station in the area to receive data from the satellite. Each ground station provides essentially a few thousand-mile window of reception around it. So I don't know how much this is going to mean to you guys. I think I'm assuming some of you are software engineers. But I always like to do a little bit of groundwork before I hack a target, just to get the general idea of their security posture. So I was poking around on Global Star's website, seeing what I could find, and was having some issues logging into my account. All of a sudden, I tried to log in, this error popped up. And for those who are familiar, it's a SQL injection, potential SQL injection. So for those unfamiliar, it could be used, it's kind of a result of sloppy programming and potentially could be used to compromise your website. So at this point, I'm getting that kind of warm, fuzzy feeling that, hey, they're kind of sloppy, this is going to be a fun target to hack on, we're going to find some good stuff. And I kept digging deeper, and it turns out that the data that's received by the ground stations is forwarded over FTP and HTTP. Yeah, there's no S on there. That means the data is not encrypted. So it may be easier just to sniff this data flying over the internet, but that's not as fun as like intercepting actual satellite data. So it seems like they're cutting a lot of corners here on this whole system. So things are looking pretty good in general. So let's dig a little deeper and do some intelligence gathering. So where do we look for information on Globalstar's system? It's a closed product. There's not really a lot of information on how it works out there. Obviously, Google's the natural choice. I'm a big fan of the FCC database. I don't know if you guys have poked around on there, but when people release RF products, they release a lot of really interesting spec sheets and really give away a lot of their secrets of how the device works. So that proved to be a wealth of resources for reverse engineering the system. As well as there are a lot of academic papers written on the Globalstar constellation. And I even found a bunch of leaked integrator spec sheets that were leaked online that proved to be very, very helpful. So, there's information out there. And before I started hacking, we needed to make sure someone else hadn't already broke the system. So it turns out, pretty famous hacker, Travis Goodspeed, had looked at the Bluetooth protocol of one of their spot devices, or one of the spot devices. And a guy named Natrium42 looked at the GPS to microcontroller interface. And they really did some cool work there, but it didn't really attack the satellite system itself. So I wanted to dive a little bit deeper and try my hand at something a little lower level. So looking in the FCC database, I kept seeing references to this thing called the STX3, this chip, coming up. And it turns out it's one of the transmitters used by, and designed for the simplex data network. And it was designed for integrators to put into their creations. It's low cost, low power, and tiny. You can see it there. It's the size of a quarter. And that's the device itself that does all the talking to the satellite. And there's some nice diagrams associated with this device that reference its inner workings. I kept seeing this DSSS and BPSK coming up. But I really had no idea what that meant. I was new to the RF world. But we'll talk about that more in a minute. So looking at the SCC database a little more, it came up with a bunch of frequency ranges for Globalstar's network, and then I found specific frequencies for the simplex data network. In this case, the devices we're looking at operated about 1.6 gigahertz. The devices we're looking at today are on channel A, 1611.25 megahertz. So kept digging and found this leaked manufacturer spec sheet from this company Axon. And it's a company that used to make transmitter chips for the simplex data network. And I referenced all these parameters that I couldn't help feel like were important, but again, I didn't really know what they were. So kind of the summary of the doc is that we see that DSSS again is something called a 255 chip PN sequence at a rate of 1.25 megachips per second. And then a reference to a data rate of 100.04 bits per second. It turns out these are all parameters for a spread spectrum system, but we'll dive into that more in a minute. Just keep them in the back of your head. So first, before we start diving into spread spectrum, we need to kind of review waves and modulation and RF stuff. So remember that radio signals are transmitted on radio waves, and data is encoded onto waves by modulation of various parameters of the wave. So remember that waves have three main characteristics that we can modify. They have the wavelength, essentially the frequency, how many cycles per second of the wave. The phase, kind of the position of the wave relative to a reference, and the amplitude, the height or the strength of the wave. And we can look at waves in a few different ways. And you're probably familiar with maybe the time domain representation, where time is on the x-axis and amplitude is on the y-axis. But often when working with signals, we look at the frequency domain representation, where frequency is on the x-axis. So essentially, this shows us what frequency components make up a signal. If you looked at the frequency domain representation of a pure, let's say, 100 kilohertz sine wave, it would show up as kind of a sharp spike at the 100 kilohertz point on the graph. So oftentimes, signals contain many frequency components. They're never just a pure wave. And so this graph will take on a unique shape, and that shape is often very indicative of certain types of modulation and helps us kind of understand better what's going on. So let's start and see how analog modulation is done. We're going to look at both AM and FM, which you're probably familiar with from maybe your car radio. So to send an analog AM signal, essentially you have a carrier wave at the desired frequency, shown up there on the top. And the amplitude, and you vary the amplitude of this wave according to your data, which we're going to call the modulating signal. And the resulting signal is what gets sent out over the air. Now notice how we varied one parameter in this case, the amplitude, to send out the data. Instead of modulating the carrier analogically, we could also have modulated it digitally to encode, instead of high amplitude or low amplitude, to encode digital data instead. And the method of sending digital data over AM is often referred to as on-off keying or amplitude shift keying. And we can do the same thing to frequency modulate data, except that we vary the carrier's frequency according to the modulating signal instead of the amplitude. And again, we could have shifted it between two or more distinct frequencies to digitally encode these data symbols as well. And that's known as frequency shift keying, or FSK. So we talked about the digital AM is ASK or OOK, and digital FM is FSK. We can also vary the third parameter, the phase, in a manner that's called phase shift keying. And using phase shift keying, we can digitally encode data on a wave as well. So for this talk, we're going to talk about, we're going to focus on BPSK. Remember, we saw that reference in that spec sheet earlier. It stands for binary phase shift keying. Basically, it's alternating a wave 180 degrees in and out of phase in order to encode binary data. So 180 degree phase shift is simply achieved by flipping the wave upside down or just multiplying it by -1. So here, each cycle of the wave corresponds to one symbol, a bit in this case. You can see it kind of flip for each bit. Okay, so that's kind of a rough overview of the how signals are modulated. So let's kind of go one step deeper and look at spread spectrum signals. So what is spread spectrum? Basically, it's a way to take a narrow band signal, one that doesn't take up too much bandwidth to transmit, and spreads it out over a much wider frequency range. This gives it the ability to be much more jam resistant and introduces a property called processing gain. Essentially, the more you spread a signal, the more gain you get at the receiving end. Essentially, it lets you transmit further. This processing gain actually allows for a spread spectrum signal to be received even if it's below the noise floor. This is most commonly used in GPS. So spreading a signal also allows for what's called CDMA properties. This stands for code division multiple access. And what this means is that multiple devices can transmit on the same frequency at the same time. Think cell phones. And this is achieved through each device having a unique, what they call spreading code. Remember, we saw something earlier referenced, I think it said a PN code. This is the same thing. So there's two main types of spread spectrum, DSSS, direct sequence spread spectrum, and then there's FHSS, frequency hopping spread spectrum. And the difference is that DSSS operates around one frequency. You can see the single peak there on the left. And FHSS hops between multiple frequencies, so you can see the 4 peaks there on the right. For the sake of this talk, we're only going to talk about DSSS. And remember, we saw that referenced in the spec sheet earlier, so that's why we're looking at it. So to create a DSSS signal, in this case, a relatively slow signal, 100 bits per second, it's mixed with a very, very fast pseudo-random signal. And the resulting signal contains all the information of the original, but is spread out over a much larger bandwidth. So here you can see the data BPSK signal there on the left, that's spread out, which is then spread to 1.25 megahertz on the right. That's 12,500 times larger, but they look relatively the same, and they contain essentially the same information. So let's see here. So let's take it back a step. Here's an example. Our data signal is really just 0 and 1 modulated very slowly in this case, up there in blue. Our pseudo-random sequence, it's a binary signal that changes at a much faster rate, a much higher frequency. That's our green signal there. And we mix those two together, and the resulting signal has the high frequency components of that pseudo-random signal, but still contains the information of the data signal. But so how do we recover the data if we're just mixing noise into it? Well, we simply mix the output signal back with that pseudo-random number sequence one more time, and the original data falls right back out. So now a little bit more about these PN sequences. I guess the definition would be they're strong, or they're periodic binary codes that have strong autocorrelation properties, meaning that they're a binary sequence that repeats over and over again. An interesting piece of information too is they're commonly generated with linear feedback shift registers. So for this research, we're going to be looking at a type of PN sequence called an M sequence. Again, we saw that in the original spec doc. What's interesting about M sequences is that they correlate strongly with themselves at a phase shift of 0, but very poorly at any other phase shift. So let's take a look. So here we're comparing a very short M sequence, 0, 0, 0, 1, to itself, and it has a perfect autocorrelation, or has a perfect correlation of 4. But for any other phase shift, we shift it once to the left, twice to the left, 3 times to the left, the correlation goes to 0. That's really nice because we use this to help search for that PN sequence in a signal. It makes it very easy. So let's talk a little bit about decoding theory. It's simple in theory, but decoding is actually kind of difficult in practice. In theory, you simply mix the signal being received with the appropriate PN sequence, and the data will just kind of emerge. But in a perfect world, our transmitter and receiver, they're not exactly in sync. They're not going to be tuned to the exact same frequency. So we need to accommodate for any frequency differential. Also remember that if the PN sequence isn't properly aligned with the PN in the data, then this won't work. We'll get a garbage signal out. So we need a way to align the two PN sequences. So keep on thinking how we might do that. But I'll give you a hint. We use the autocorrelation properties of the PN sequence to kind of line that up. But we'll talk about that more in a minute. So we kind of have the theory down, but we need to put it into practice and actually test all this theory out. I have no idea if it's going to work at this point. So we need to build some hardware. So to do this, I use a software-defined radio along with Python and GNU radio to do most of my code. I needed an appropriate antenna too. I ended up getting one off of eBay, like 50, 60 bucks. So for those of you that wish to try this at home, you can buy one off eBay, or just note that Global Star's antennas are left-hand circular polarized. But that's a little bit out of the scope of this talk, but you just need to have the right kind of antenna. And for those of you familiar with RTL SDR, I'm not sure it can be used in this application, as it doesn't really cover enough bandwidth. I think most of the receivers cover around maybe 2 megahertz. We need to cover about 2.5 megahertz of bandwidth to do this research. But I actually haven't tried, so I'd be curious if any of you guys give this a whirl. We also ended up needing a low noise amplifier for receiving kind of the weak signals, and supporting cabling and voltage regulators and stuff to supply it. I got the LNA from a company called Mini Circuits online. They got some really cheap products that are apparently really good. So at this point, I packaged it all up into a nice box because all these parts are kind of fragile and hackers are clumsy, and I didn't want to break the expensive toys. So I mounted the antenna on the outside so that I can aim it appropriately at whatever we want to target. I took it up in Vegas, and you had it up in the hotel room pointing at McCarran Airport and all around. So it's nice and portable. I'll let you guys take a look later. But anyway, so how does this hardware work in general? How does this software-defined radio hardware work? It listens for radio waves, analog radio waves, and converts them to digital data that our computer can process. It does this by taking samples of that wave. So this guy named Nyquist, back in the day, like way back, he came up with the realization that while sampling, you need to sample at least twice as fast as the signal's highest frequency component in order to represent the signal accurately. So a real-world example of this, to maybe help you wrap your head around it, is that the human ear can't really hear frequencies higher than 20 kilohertz. If you look at a CD, the CD audio is actually sampled at 44.1 kilohertz, just over twice the human hearing range. So you should also know that the software-defined radio hardware uses what's called IQ sampling, or IQ modulation, to receive and send signals. And this topic's a little bit out of scope for now. But you should know that for each sample taken, 2 values are recorded, an I and a Q value, and has strong benefits for processing signals in software. If you're interested, I suggest you guys take a look at this YouTube video. It's absolutely fantastic for explaining this, much better job than I'll do. The bottom line is you don't really need to understand this for the scope of this talk right now unless you are giving it a whirl yourself. So the first step to decoding satellite transmissions is to figure out this PN sequence, this kind of mystery code, if you will, that we don't know that's critical to intercepting the data. So we're going to put this hardware to work to kind of figure out what this is. So remember that we're looking for a signal, the PN sequence, that's 255 bits in length, and it repeats over and over and over and over again at a rate of 1.25 million chips per second. I should mention here that a chip is the same thing as a bit, but we name them differently so that we can distinguish them from actual data bits. So now, interestingly enough, we can treat DSSS BPSK signal the same as we treat BPSK. And check out this graph. I'll try to explain it. But we can see that the BPSK signal shifts the wave at its transition, but once every several cycles. The TSSS BPSK signal shifts this wave much, much faster, but in the same way as the original BPSK signal. So this means that we can use an ordinary BPSK demodulator to receive the spread data. Now, the downside of receiving data this way is that we don't receive any of the processing gain from the spreading signal. So this technique really only works over short distances, but it's perfectly legitimate. I've tried it across the room, a couple hundred feet away. It seems to work all right, but it doesn't really work far away. So to accurately receive the data, we need to set our hardware to sample correctly. And we have to meet a couple different criteria. First, the USRP I'm using will only sample it at multiples of, factors of 32 megahertz. We also need to sample at least twice as fast as the highest frequency component, which in this case is the PN sequence, 1.25 megahertz, due to Nyquist theorem. We also need to sample at a rate that provides an even number of samples per data symbol. In this case, an even number of samples per chip. We achieve all this by sampling at a rate of 4 megahertz. You can see by the little math to scratch it out. And then resampling the signal, essentially interpolating data points in it to get a resulting upsampled 5 megahertz signal. And what's special about this 5 megahertz signal is that it has a sampling rate that corresponds to 4 samples per symbol, nice and even. So this works well for us. But how do we get recover the actual PN sequence? Well, we know from doing some calculations that the PN sequence repeats 49 times for each bit of data. And the PN sequence doesn't cross any bit boundaries. So if we XOR the PN with a fixed bit of data, the result is the PN code itself. So let's use GNU Radio to decode the signal as BPSK with the appropriate settings and output the data to disk. So I'm just outputting data through a BPSK demodulator to a binary file. So here you can see a GNU Radio flow graph. I used to do this. And you can see that the PSK demodulator includes a setting of 4 samples per symbol, like we talked about. The PSK demodulator outputs the decoded symbols to a binary file, which we can then examine. So looking at the data in a hex editor, we can clearly see that there's a repeating sequence of data, 255 bits in length. So yeah, that ended up being the PN code. It turns out this is kind of the keys to the kingdom. This code is used by all the simplex data network devices to encode their data. So now that we have the code, we need to actually to spread the data. You might recall that we need to mix the PN code with the incoming data to retrieve the information. And if all goes well, we should expect an output signal that will contain a very strong narrowband signal, shown as a sharp peak, similar to the bottom right illustration. So above is what a normal simplex data network transmission looks like, and the graphic below shows what hopefully it'll look like when we despread it. But before we begin, it's important to know that working with these signals is very computationally intensive. Receiving a signal at 4 megahertz with a software-defined radio, it works out to a data rate of like 30.5 megabytes per second of data that we need to process. So for the purposes of this work, we're recording the data and post-processing. I think eventually it'd be possible to use more robust custom hardware, maybe FPGAs or use CUDA to do this work. But it's kind of a big pain in the butt, and it's a problem for later. So a couple coworkers and interns helped me out. Previously, it'd take about a minute to process one data packet, but we've got it down to about 10 seconds now, including disk I/O. So how do we despread? First, we need to lock on to the mixed PN sequence in the signal. And we do this by correlating the received data against the recovered PN sequence at each point in time. Essentially, we're sliding the PN against the received signal and correlating. If we plot those correlations perfectly over time, when the PN is perfectly aligned, we'll see a sharp spike indicating that we're in alignment. And this is how we know when to mix the two signals together to despread the data. So if we only align the PN on the first correlation spike, due to some frequency mismatch, we'll fall out of correlation over time. You can see here on the graph on the left. And so we need to fix that. And we fix that by adjusting the PN forward or backward at each and every correlation peak to ensure that it's in perfect alignment. At this point, once we're in alignment, we can mix the data together, and hopefully the correct data will emerge. So let's give that a whirl. So after compensating, you can see on the left there that the correlation over time stays relatively constant with a slight oscillation. I don't really know what that's from. If we zoom in and look at the correlations over the whole packet, you can see negative and positive correlations there on the right. And these are actually representative of data bits in a spread spectrum packet. So if we look at the signal coming out of our software despreader, up there on top, sure enough, we see a sharp spike in the middle. And that really is kind of indicative that our despreading worked. And this means we successfully despread the data. Zooming way in on that peak, we can see the waveform looks like a BPSK signal, and it's operating at about 100 hertz there. So we know this is the data rate in question that we're looking for. So we're feeling like things are working out all right. So let's try to, let's see here. Yeah, let's try to actually maybe, if this worked, decode some data packets. So if you look at the time domain representation of this signal, we can actually see data bits coming out over the air. I was actually shocked when I first fired this up. So now we can clean up the signal, namely just low pass filter it, and then pop this into the PSK demodulator, and hopefully we'll get data. So at that point, a bunch of random data fell out. I got this data stream of just binary garbage at the top. But we need to figure out a way to validate it. So I found a spec sheet online that references kind of the rough data packet format for the networks. And it starts with the preamble, essentially a constant, unique binary sequence that tells the receiver when a packet's starting. And then the data packet has a manufacturer ID followed with a bunch more data in it. So if we convert the manufacturer ID, the first, was it like 28 bits there, to decimal, sure enough, it actually lines up with the serial number on the back of the device itself. So this is a clear indication that we're doing something sort of right. We're actually getting real data. So now the data packets contain just about any sort of information, and that's up to the end integrator. But these devices are predominantly used for location data. And it turns out that everyone uses the same format because they want Globalstar's backend to be able to decode their information for them so they don't have to handle it. So after extensive comparison, and my interns spent a lot of time on this for me, they found out that bits 8 through 32 are latitude, and bits 32 to 56 are longitude. So simply you convert the binary to decimal, and then multiply the resultant value by a decrease per count value, and extract the actual latitude and longitude from the data packet. I've got kind of the rough Python code listed here, but it's all published online if you guys want to take a closer look. So the data packets also contain a checksum, which will let us actually validate that the data is what we think it is. In short, I figured out how to calculate the checksum, but that means we can not only validate packets, but we can create our own. So we figured out that there's no encryption, no signing, or any other data protections, so we can really now inject our own data packets back into the satellite network, or there should be nothing stopping us from it. So now recall that we're currently just receiving data on the uplink. And due to the bent pipe nature of Globalstar satellites, the data on the downlink is exactly the same as the data on the uplink. So reception on the downlink is going to be very similar. Except in this case, on the downlink, we'll need to compensate for Doppler shift, multipath interference, and other stuff like that. So this is an avenue for future research I'd actually be very curious to talk to some of you guys about. All right, but so now that we think we can create our own data, can we inject it back into the satellite network? Maybe. So a little warning, don't transmit on Globalstar's frequencies. It's probably illegal to do wherever you live. It might interfere with critical emergency communications. Fortunately, the simplex frequencies aren't used for satellite control itself, so you're not going to bring down a bird. But no one likes the FCC stalking them and coming to their house late at night and throwing them in jail, so just don't. But if you wanted to, that's actually the really easy part. You simply mix the data, the PN sequence, and the carrier together at the appropriate rates, and you just send it out. And all you need is about 0.2 watts of power. These things talk to 500 miles into space on 0.2 watts. It's crazy. And you can get an appropriate amplifier on the internet for what, $200, what I paid for that one. I ended up writing some GNU radio code, kind of hacked together, but it works, and it'll modulate our data that we want to send. But what if there's an easier way? So Globalstar provides an OSX firmware update utility for their spot trace devices, these guys. And inside the application package, there's a tool, Spot3 firmware update.jar tool, that contains all sorts of interesting functionality, but it's never called by the consumer app. It's just functionality baked in and never used. So I forget what it was, but inside the jar, there's this debug console.class and this spot device.class. But one of these contains a method called write ESN, electronic serial number. So we write a little Java utility there on the right to call this method in the jar. I think I actually called the debug console.class. We pop a debug console that proved to be very handy. It's a little hidden functionality. And this debug console actually let us update the ESN. So essentially, we can change the serial numbers of any of these devices, or possibly clone a target's device or whatever. So to prove this, I cloned one of my spot trackers with the ESN of the other one and turned it on, told it to transmit. And sure enough, I got tracking information back in my email confirming that it was cloned. So they found out about this and they quickly patched it out. But I've got a copy if any of you guys want to try this at home. But I've got all my spot devices running off one account, so it's a cheap way to use the functionality. So besides the obvious of using the network to transmit your own custom data or expanding the capabilities of your service, such as sending out packets faster than you're supposed to, or what can an attacker do with this transmission functionality or transmission capability? Well, first, these devices are used in emergency response everywhere. What if an attacker spoofed thousands of false emergencies and jammed up the emergency response center and prevent aid from getting to someone in an actual emergency? What about monitoring for help requests and just canceling them? Just why not? So I talked to a pretty well-known reporter who was a correspondent in the Middle East for about 10 years. And she said that her and many of the other journalists over there use these spot trackers to monitor their whereabouts in case they're kidnapped. And so they were relying on these things for their lives. But in reality, foreign intelligence could just as easily be listening on this unencrypted data. So that's kind of a scary thought. So none of them are using these anymore, it turns out. So it also turns out these chips are used in access control system, by law enforcement, even for animal tracking. I personally think it'd be kind of funny to spoof the location of a grizzly saying it showed up in downtown San Francisco, and, see what people think. But it's also used heavily in SCADA systems. I'm going to refrain from naming specifics. I don't know what you guys are going to do with this information, but especially for like water quality monitoring and pipeline monitoring, and even big oil and gas operations use this to monitor their data. What if you were a rival oil company and you wanted to figure out where your competition was drilling? Maybe you just fire up your own homebrew base station and just listen for your competitors' assets. It's worth a shot. But wait, there's more. So Lockheed Martin Flight Services, the contractor that handles flight planning for the FAA, just allow these devices to be used to track any VFR flight. So what if an attacker made an airplane to appear to deviate from a flight plan into tightly controlled airspace? You might jam up SFO for a while, or worse, maybe cause an accident. So to demonstrate some of this, I built my own full-featured capability. And the way it works is that I sit with the device in the uplink path of the transmitter and listen. And over time, I'm able to pick up countless transmissions from asset trackers and map their pattern to life. This makes it really easy to identify what a target is, kind of by where it goes. In this case, you can monitor, let's say, an armored car route and just watch its path back and forth every day and know exactly where it is. And now that I know where the armored car is, I know when to hijack it. So I hijack the car, disable the beacon, and begin spoofing their beacon's ID with my transmitter. And I spoof GPS coordinates so it looks like it's en route, but in reality, I'm driving somewhere else with all the gold. So you might ask, does this work? And short answer, yes, but we needed a high vantage point. So the only real solution, clearly, was to go out and learn to fly so we could fly this capability to intercept data. So that's what I did. Went out and got my pilot's license, and I've been flying this thing kind of regularly, trying to intercept data from the air. Every time I have a chance to get on top of a tall building, I'm sniffing data packets. It's pretty interesting what you see flying over the air. So I'll give you guys kind of a quick demo of how this works. I decided not to tempt the live demo gods here, but I've got a little video, and I've kind of broken it up short step by step here. So let's drag this over. Full screen. So here's our GNU radio flow graph. We're going to fire it up. And we can see here we're listening for a data packet. We see a data packet. We capture it to file automatically. And then it kicks it over to the processing. Let's see. And then we go ahead and process the file. And it takes a little while to do. I think I cut through the processing here really quick. I'm going to fast forward. So we've locked on. We've caught the correlated the PN sequence. We're locked on, and we're despreading. So it takes about a minute to do with this revision of the code. And boom, we see a nice, strong correlation across the board. Then we take a look at that despread data. We see that sharp spike in the center. We're just replaying it. That's indicative that we despread properly. And we're going to zoom out here in the time domain representation. You can see the actual data bits from the satellite packets flying over the air. And then, let's see. We're going to output those data bits from that to file, and we're going to analyze the file. So we do that. We get a binary sequence indicative of a packet. We run that packet through the decoder and the checksum. And bam, we have like the manufacturer, unit ID, message number, and then other data on the network. And I have further code written to process the user data there to pull out the coordinates and such. So this is all online if you guys want to give it a whirl. Let's see here, where'd my mouse go? So all right, a few parting thoughts. I disclosed this kind of bug or issue to GlobalStar about 180 days before I presented it. And they were pretty friendly and seemed pretty concerned. And I provided in-depth technical details and hopes of helping them, and never heard back. After I broke the news to the public, they issued a statement saying that they take their privacy very seriously and that they have monitoring to detect attacks like this in place. But unfortunately, half this attack is passive, so it can't be detected. So I don't know how they monitor that. In the transmitting portion, well targeted, really there's a low probability of being detected. So in some of their recent statements, they were quite defensive. They called me some names, issued a big press release, and it's kind of sad when we see manufacturers acting this way when there's a legitimate problem that really could be fixed, and I'm happy to help them fix it. But so hopefully they're serious about fixing the issue and will. I really hate to see the vulnerabilities like this used for bad out in the wild. So we'll see what happens. There's been really no fix yet. So there's still a lot of work to be done on this. I don't know how much further I'll take it. But my code's on GitHub if you guys want to take a look. Apologies, it's kind of messy, very much proof of concept stage. But I'd really love to collaborate and maybe start intercepting signals on the downlink if any of you guys are interested or have experience in signal processing and scaling up the computation. I think we're really only at the tip of the iceberg on what data we can see flying over the air. But with one base station, we'll be able to see for about 4,000 miles. So that's kind of my next goal, is to build one base station, just see what we get. So if you're interested, please help out or come, give me your advice. So a couple conclusions. I still think GlobalStar makes a great product. These things work very well. But for manufacturers, if you're manufacturing kind of these SATCOM systems, remember that the aerospace products and satellites, they've got a long life cycle, and we're stuck with them for a really long time to come. And the way the GlobalStar system is implemented, it's not really patchable. These devices don't really support firmware updates, and they're so far out in the wild that they're never going to see a firmware update. So really the best thing going forward would be to add an optional layer of encryption on top of this, and then somehow implement that in the back end. Consumers, just remember that, or hold manufacturers to a higher standard and ask to know how your data is being transmitted. They don't publish that it's not encrypted, but they're not saying that it is either. So look into the systems you use. So special thanks to my interns. They helped a lot with the testing and all that. They've all gone off to school, but they were a huge help. Let's see, yeah, so questions, comments, code's online, slides are online. Follow me on Twitter, got some more interesting stuff coming out. Feel free to email me if you guys want to chat more, but questions, comments?
Question.
Yes, sir.
Location service, is it really just latitude and longitude at a NOR height?
For the system itself?
I mean from the system that's available to those systems. Do they just have no data on height?
The GPS chip in these systems does have data, but it's not being relayed in this specific implementation. There's no reason it couldn't be, but the protocol is just set up. There's not really enough room in the data packet to shove that information over. Yes, in the back.
So, have you found anybody sending data that isn't just that long with the trackers and the tracker?
Yeah, so the question was, have I found any data being sent that isn't just latitude and longitude? And the answer is yeah. This system is used for all sorts of crazy custom implementations as well. And the real issue is there's really no metadata or anything to tell you what's transmitting other than going and tracking it down. Or maybe finding some manufacturer spec sheets, but these are really kind of integrated in custom enterprise applications and things like that. So other than just kind of correlating a lot of the data and trying to decode random bits, we're not really sure what those things are. But you look at enough, I'm sure you'll be able to figure it out. Yes,
Along
right.
that same line, is there anything that you found just interesting or odd, data, plain text, or anything like that?
The question is, have I found anything interesting or odd? The answer is no. I haven't really seen any plain text data or anything going over the area. It's really mostly just been location services. Granted, I have a pretty limited sample size because I have had trouble getting high enough and then long enough and in really densely populated areas. So hopefully with the downlink reception, we might be able to do a little bit more of that. Yes, right there.
Do you have any idea how costly it would be for them to fix this?
Fortunately, they don't have to replace the satellites. They're going to have to replace or recode a lot of whatever their downlink reception infrastructure looks like. I don't know, but it can't be cheap. You know, I think the easiest way would be to have just like a new revision of devices that implement kind of an extra layer of encryption, and then you know, implement that in the back end, and kind of just accept that there's a bunch of legacy systems out there, and just kind of, you know, make the best going forward. So truthfully, I think they've kind of fallen on hard times, is what I understand, and I'm not sure there's going to be a lot of development going forward. So I don't expect to see a fix, but maybe they'll prove me wrong. Yes, sir.
So it seems like all these band pipe systems, they have to have actually PMD correlation at the satellite because they're transmitting and receiving different frequencies, right? So they actually have to have that being encoded.
So actually, no. So actually, no. There's no decorrelation or anything done on the satellite. All the correlation and despreading is done on the ground. So because there's a bunch of different other systems that operate through these bent pipe satellites, they just kind of shift the frequency up, or shift the data up in a frequency or down a frequency to downlink it. What's interesting is this actually means you could use these satellites for your own purposes as well. Like if you could spread your own data with your own unique PN code, you know, if you want to do some covert communications, shoot up the satellite, receive on their downlink, and you have your own satellite network. There's nothing stopping you from doing this other than the laws. And you know, there may be ways to geolocate you, but you know, if you're far enough below the noise floor and transmitting, you know, at random times, chances are no one's going to catch you. So I didn't say this, but you know.
What do you mean you didn't say that?
No, it's bad advice. Yeah, so theoretically, all the reception is done on the ground. All right, well, feel free to, you know, ping me, email me, can ask questions later. But oh yeah, one more.
The only thing you mentioned that you had found some pretty good resources for learning all the different phases, and that's a lot of stuff you went through. It'd be rad to see like a summary of your top, you know, a couple of lists of some of that stuff, just so I could retrace some of your steps.
Yeah, thanks for bringing that up. So I actually have intended to get a list up on the GitHub. I will try to remember to do that. If not, you know, ping me directly, and I will get you resources or even just chat with you. I'm really happy to chat. I don't have a ton of time, but I've got a couple of people working on this on the side. So yeah, I'll do my best to get some stuff up. But you know, Google's your friend, and just keep beating your head out until it works. I found that, you know, things are, just follow your intuition, and things kind of tend to work out. So. Cool. Thanks, guys.
Thank you very much, Colby.
I've got the hardware. You guys can take a look at some point if you want.
Yeah, this is great. Both our speakers have something tangible that we can take a look at. So